saw how to quantize the Dirac field and realized that it describes fermions. So let me remind you how it works, if I can find some chalk. Okay. Anyway, so the way it works is that we solve the Dirac equations, and then we find some set of orthogonal wave functions. So the coefficients of these wave functions are interpreted then as creation and annihilation operators, and the creation operators are those that multiply positive energy modes, and the annihilation operators, thank you, David, they multiply the negative energy mode. So this is completely analogous to the Clay-Gordon field. So in the Clay-Gordon case, when we solve the Clay-Gordon equation, well, the solutions are just plane waves, and for some reasons, we wanted to normalize them such that they square to twice the energy of the wave. And so these are the two types of solutions that we found. Okay. Now, for the Dirac equation, well, the story is absolutely the same. So, but now the Dirac field has an index. It's a spinor. So there will be, for any plane wave, there will be two independent solutions, as we saw. So we denoted them as U alpha S of P e to the IPX minus IPX, I suppose. And then Vs alpha of P e to the plus Px. Again, the amplitude square to square root of twice the energy, or actually without, anyway, so they square to the energy. And so the coefficients in front of, so these are the basis of functions that we use. We expand our field in this basis and interpret the coefficients as creation or annihilation operators. Then we started to discuss chirality and helicity of the spin of massless Dirac fermions. So let me remind you that we have introduced the fifth Dirac matrix, which is the product of all of them. So this matrix has the following properties. It anticommutes with all other Dirac matrices. And it squares to 1. So if you take well, this combination, then this will behave as projector, and this is what we call chiral projectors. The explicit form of the gamma 5 matrix is log diagonal. So what this projector does, it leaves only upper or lower components of the spinner. So psi left, which was defined by applying the projector with a minus to the 4-component spinner, gives the spinner that only has upper components. And this we call left-handed. Two-component spinner, and two-component spinners are usually called wheel spinners. Likewise, we can define the right spinner if we take the opposite sign in the projector. Which then leaves only the lower component. So this would be the right-handed spinner. Yes?
Is there some reason why we associate the word left positive velocity and the word right negative velocity?
Well, left and right is a matter of convention, of course, but the reason that they have handedness is that for the massless particle, chirality coincides with helicity. And helicity is naturally is the handedness, so it's the way spin would rotate as compared to the direction of motion.
Just wondering if there were a reason for that convention.
No, there's no particular reason. I mean, there is complete symmetry between left and right. It's just two words that denote them. Anyway, so one question that we can ask is if you could live only with left or right spinners. So relativistic invariance suggests that yes, we in principle could consider the theory where only left spinners are present, because they transform through just among themselves under Lorentz transformations. So Lorentz transformations in this 4-dimensional spinner basis are block diagonal. So the representation of the Lorentz group is reducible. And in fact, is a sum of two representations, one for left spinners and one for the right spinners. Now, what mixes them is parity transformations. As you see, or as we have seen last time, the gamma 5 matrix is a pseudo, so it behaves as a pseudoscalar. What it means is that it is invariant under Lorentz transformations with positive determinant. And the determinant can be the plus or minus 1. And then change sign under parity. So parity is denoted. This is a transformation that maps a 4-vector to the 4-vector that has the same time component, but but it sort of makes a mirror transformation on the spatial components. So this obviously doesn't belong to this class of transformations because the determinant of this is -1. So quantities that change sign under this type of transformations are called pseudoscalars. And so gamma 5 is one example. Another example that you may be familiar with is the scalar product of electric and magnetic fields. So magnetic field is a pseudo vector, and electric field is a vector. So if you take a scalar product, you get a pseudo scalar. Okay, so but let us see sort of more, give a more formal argument why we can define a theory with only right or left-handed fermion. Well, we have seen that the Dirac equation indeed decouples, so the left-handed fermion satisfies an equation that is independent from the right-handed fermion. And moreover, this equation just tells us that, that on shell, so for a massless fermion, on shell, the Dirac equation, so on shell means that it satisfies the Dirac equation. And on shell, left and right components live independently. And the Dirac equation for them just means that their helicity coincides with chirality. So the Dirac equation is basically the statement that helicity is equal to 1/2 of chirality. So helicity is the projection of the spin on the direction of motion. And chirality is, chirality is defined by these projectors with the gamma 5. So from that, you also see that for a massless particle, helicity is Lorentz invariant quantity because chirality is Lorentz invariant. Now let's see how the theory of single left-handed fermion would look like. So the Lagrangian that we would write is then contains only left components of the spinor. So let's just look at this massless Lagrangian and see if it's a consistent, a consistent Lorentz invariant expression. So, in addition to psi left, it contains also the conjugate spinor. So let's see how the conjugate spinor is projected. So psi left bar is equal to what? Oh, it's psi left dagger multiplied by gamma 0. And psi left, by definition, is 1 minus gamma 5 over 2, acting on the psi. So in principle, we should take a Hermitian conjugate of this matrix, but this matrix is Hermitian from the start. It's clear from its explicit form. So it's the dagger of it is equal to itself. So now what we do is we commute it to the right through the gamma 0. what happens is that this sign will then change because gamma 5 anti-commutes with gamma 0. So therefore, what we get is psi dagger, gamma 0, and then 1 plus gamma 5. So this is psi bar, and then 1 plus gamma 5 over 2. So when acting on the Dirac conjugate spinor, the sign of projection changes. So let's see what does it imply for the Lagrangian. Well, we substitute here this expression with projectors. And then we commute one of them to the right through the gamma mu matrix. Again, gamma 5 anti-commutes with every gamma matrix, so we will change the sign. We'll get the sign changed when we do this. Yes? Yes. So this shouldn't be there. Thank you. Although formally this equation would also be correct because projector acting twice gives the same. But what I really wanted to write is this equation. So, okay, then we can anti-commute 1 plus gamma 5 to the right. The sign in front of gamma 5 changes. And we get the projection, the projector squared, which, well, again, is the same as the projector itself. So we'll get the Lagrangian of this form. And this is how it's usually written. So this expression is manifestly Lorentz invariant because it's a sum of, you can write it as a sum of two terms. One is just the original, well, the usual Dirac Lagrangian, and the other the Dirac Lagrangian with the gamma 5. So under Lorentz transformations, it will transform as a pseudoscalar. So this, to conclude, this Lagrangian is Lorentz invariant. But breaks parity. So, well then, why don't we add the master? Let's try to do it. So we may start with the Lagrangian that contains the mass. And so the mass term in the Lagrangian, which will be written as psi. Let's give a simple try to this expression. Okay. So what this would be psi bar 1 plus gamma 5 over 2, 1 minus gamma 5 over 2 psi. And you see that here we have orthogonal projectors. So which then kill each other, and so we get 0. So we cannot add a mass term to at least of this form. So let's, look what happens if we write this expression. And also, well, we can do this calculation simultaneously for the two cases. But then these projectors will be the same, right? And so this will be equal to psi bar 1 plus minus gamma 5 over 2 psi. So in particular, if we add the expressions with the, well, plus or minus interchanged, we'll get the mass term in the original Dirac Lagrangian, which we can then write as psi right, psi bar right, psi left, plus psi left, psi right. So now you see the reasons why we started with 4-dimensional spinors and not 2-dimensional. So the one reason was that we wanted to have a theory that is parity invariant. So electrons, to some approximation, do not break parity. And second, we wanted to have massive fermions, and to formulate a theory of massive fermions, you need to combine the left and right spinors. And so you better start with just with the psi without doing any projections. Is it clear? Are there any questions at this point? Yes.
These tests over here correspond to a mass term because in Lagrangian that would be just multiplied by n?
Yes. Well, however, there are, well, particles in nature that are described by this type of Lagrangians. So namely, neutrinos are intrinsically left, or, well, are intrinsically left-handed. So they're described by two-component fermions. And, well, so this Lagrangian would be, to some approximate, to the first approximation will give us a theory of neutrinos. Now, of course, any truth has several layers to it. So, in fact, neutrinos do have mass. It is possible to write down a mass term just using psi left or just psi right. So this is called the Majorana mass. But in the first course of field theory, I wouldn't like to describe it. Now, the second truth is that even for electrons, the parity is broken. But it is broken by interactions. So electrons, they can be in two polarization states, in left and right states. So their mass term has this form. But when it comes to weak interactions, then left and right components of the electron participate in them differently. But weak interactions are very feeble. So parity violation is actually very, very small and leads to extremely tiny effects that have almost no manifestation in, microscopic physics that we basically know. So I would not go into this detail, and we'll just stop here. So this would be it for the Dirac theory. Do you have any questions? Yes.
So when you say reinteraction break parity, so what kind of process, or what is particle, or what kind of process that makes the reinteraction break parity?
What kind of process? in principle, any process associated with weak interactions is
or maybe
not parity invariant. But again, this is a small effect even. It's usually a very small effect, but well, the most well-known, most important weak interaction process is beta decay. So beta decay is not parity invariant.
Maybe I can change my question as, so why do you say, so what is the relation between the this invariant under the parity change and the parity break in the weak interaction?
Well, okay. So this describes what I was described so far are just free electrons that, well, they were just free. There's some. Each electron has a certain energy, etc., etc. To describe their interactions, we need to add some terms to the Lagrange. And so the truth is that to add the weak interaction terms, we do it in a way which is not symmetric. So in this Lagrangian, psi left and psi right enter asymmetric in a different way.
So do you mean that if you want to describe a weak interaction, you need to add the Lagrangian which has the psi L psi 1?
Yes.
So that.
Yes. So the weak interaction Lagrangian contains well, gamma 5 projection, and it acts differently on left and right on left and right electron field. Okay, so then we go on, and now we would like to quantize another type of field. This is the field that you're all familiar with, namely electromagnetic field. So our goal will be to quantize Maxwell's equations. So in principle, electromagnetic field is, well, it described, it is, Maxwell's equations can be written in terms of electric and magnetic fields. And there are, how many? I guess 6 equations. You have to write 6 equations to find 6 variables. Now these 6 equations are paired in 2 groups. And they can be written in a Lorentz invariant way. In fact, this was where Lorentz found his transformation. So he looked at the symmetries of the Maxwell's equations and found that they are invariant under what's now known as Lorentz transformations. To write them in a manifestly Lorentz invariant way, one usually introduces the field tensor. Of which E and B are various components. So they are not really components of 4 vectors, and as one might think, but they are really components of a rank 2 tensor, these 2 indices, such that its time-like components form the electric field, and the space-like components correspond to the magnetic field. In total, the electric and magnetic fields form one quantity that has two Lorentz indices. And then for this quantity, one writes two types of equations. One equation is this one. So the covariant divergence of f mu is 0. And the second equation is a combination of three terms. With the indices cyclically permuted. So if you sum the derivative of f and make a cyclic permutation on the indices, then this is equal to 0. So these are the Maxwell's equations. And we want to find, we want to quantize them. So we'll proceed in our usual fashion. So we'll find a general solution to these equations, and then interpret partial waves as creation or annihilation operators. But here there is one subtlety that we have to discuss before going on with solving the equations. Namely, in principle, this way of quantizing the field is a shortcut, and an honest procedure would start with the Lagrangian, then derive the Hamiltonian, the canonical variables, and impose the commutation relations, and then diagonalize this Hamiltonian. So for the Maxwell's equations written this way, it's impossible. It is impossible to find a Lagrangian from which they are derived. Now, I don't have a simple explanation to this fact, but it has to do with this equation. So this equation is really not Lagrange friendly. One has to change a little bit the formulation of the theory to be able to to formulate the canonical variables for the electromagnetic fields. So this is done by introducing potentials. As you know, one can introduce so combine potentials in a single 4-vector. So its zero component is the usual electric potential. Which, well, this is just the usual potential that we have in an electric socket, and this is the potential that's responsible for the magnetic fields. So from the point of view of Lorentz transformations, they form a 4-vector. And so in terms of A, F mu is written as d mu A nu minus d nu A mu. So F mu is, by the way, is an antisymmetric quantity, so it also satisfies this equation. So this is manifestly antisymmetric, and moreover, if we plug it in the equations, then this equation will become an identity. So it's not really an equation. In some sense, it's just a constraint that is solved by this parameterization. So, so this solves one pair of one set of Maxwell's equations. And then, well, we are only left with equation 1. Which you can write in terms of A. And derive from the action in which the Lagrangian is the square of f mu. If you want to write this in terms of the well, more usual variables, this is just 1/2 of electric field minus magnetic field squared. And so this is the action, the Lagrangian density of electromagnetic field. By taking a variation, one can derive the Maxwell's equations. And so this can be, we can go on and try to find the canonical variables associated with potentials. So now dynamical variables are potentials now. But what we will see is that there is, again, some problem with that. Or this problem is not, it's possible to circumvent it, but taken at face value, it looks like, well, it doesn't look like something that we have encountered before. Namely, let's see how A0, the electric potential, enters in the Lagrangian. It enters only through this term, because this would be Fij squared, and when these indices are I and j, the A0 simply doesn't enter. So it enters only here into the electric field squared part, which contains di times A0, right? So Fi0, which is the electric field, is d0 AI minus di A0. And so the electric field doesn't, so it, just by construction, it enters only with spatial derivatives. So there is no time derivative of A0 in the Lagrangian. In other words, if we would try to define Phi0 by the usual equation like that, so this would be the canonical momentum associated with A0, then we'll just get 0. So there is no momentum associated with the zeroth component of the potential. And so the A0 has a different interpretation. It's not really a dynamical variable, it's a Lagrange multiplier. So the equation of motion for A0, so the result of varying the action with respect to A0, is not really a Hamiltonian equation, but is a constraint. The reasons for these complications, so one can still proceed and describe the system as a Hamiltonian system with constraints. And there is a special theory how to quantize such systems. Again, I will not do it in all of these gory details. But it is interesting to see the reason for all these complications. Why do they arise? They arise because of the redundancy of this formulation. So the representation of the field strength, which is the physical quantity, right? With measurable physical quantity, we can definitely measure electric and magnetic fields. But the potential is not. There is a redundancy. Which manifests itself in the invariance of, well, just this parameterization under the shifts of the potentials by any gradient. So if you substitute this shift here, you see that you get d squared omega here minus d squared omega here, so it just cancels out. This redundancy is, well, we can call it a symmetry if you wish. So because this is a transformation under which the Lagrangian is invariant. So this symmetry is called the gauge symmetry. Or gradient symmetry. And in quantization, we need to take care of this redundancy and treat all the equations such as to take this gauge freedom into account. So, well, we have studied the implications of symmetries in field theories in general, but yes.
Does the gradient symmetry relate to the A naught freedom? The lack of time derivative of A naught and the Lagrangian? We said that that's one interesting characteristic of the Lagrangian, and now we're seeing that the Lagrangian is invariant under gradient symmetry. Are those two related or separate?
This is just the same symmetry, yes. Well, one possible transformation is shift of phi 0 by any time derivative of any function. Now, the symmetries that we studied before were a little bit different, because here omega is an arbitrary function of space-time coordinates. So the symmetries that we studied before are usually called global symmetries, in the sense that the parameter of transformation was either independent of x, or if it depended on x, it was very, very definite fixed function of x, like for Lorentz transformations. So here, this function is unconstrained, so this symmetry is a local symmetry. In the sense that we can change it arbitrarily in any point in space and time. Okay, so we can take whatever function we want, we can localize it in the neighborhood of any point. So it's just the local symmetries denote possibility to choose the function arbitrarily, or depend arbitrarily as a function of x. And so, so when we will solve the Maxwell's equations, we will need to understand how to take how to take the gauge symmetry into account. So let's take a very, very short break just for 1.5 minutes.